This video here is for imaginary numbers. It's part of a quadratic unit, and it's one of those things that what is an imaginary number? Why in the world would we even care about it? And the story goes, as best I know, is that math people didn't like the fact that x squared equal to -1 had no solution. There's no real answer to this. If you were to look at it graphically, x squared and its intersection right here at 0, 0, -1, it never crosses this line right here. It never reaches it. However, there are imaginary answers, and it's a pretty neat system, imaginary numbers. As we go back to this, x squared equals -1. If I square root this, imaginary numbers say that square root of -1 does have an answer. It's just imaginary. Square root of -1, plus or minus, by the way. Square root of -1 is now defined as I, which means imaginary. Got a new stylus here. I'm trying to figure this out. So imaginary. Imaginary. Okay. Okay. So anyhow, it is defined as square root of -1. So if I have, there's several things that every imaginary number can be written as a sum of a plus bi, meaning that it can be written as a real number plus the imaginary number. So like 5 plus 2i. This is an imaginary number. Or something like 7 minus 3i. These are imaginary answers. So there's actually an imaginary plane when you're talking about, the xy plane. We also have an imaginary plane, and we don't have to worry about that part. But, and again, the big thing is that square root of -1 is equal to 1i, hence imaginary. Okay, so we're going to go ahead and write some of these. So like for instance, if I had square root of -16, this is going to be equivalent to 4i, because square root of 16 times square root of -1, again starting new stylus here, square root of 16 is 4 times square root of -1, which is I. Okay, so it is the square root of -1. Okay. And as I mentioned, it's something that, when we look at quadratics and we're trying to solve them, if we're looking at it graphically, the line never intersects. That if you have that situation, there's no real answers. However, there may be no real, but there is an imaginary. I don't know if I like the stylus or not. Okay. Alright. So, if they don't intersect, there is imaginary numbers. First thing is we need to be able to add imaginary numbers. And again, this is the only time that I know of an application is actually adding imaginary numbers. And there's electrical circuits, and we're talking about ohms and that kind of thing. And the only thing I know of an application for imaginary numbers is when you're adding them. But there's some cool stuff here. Before we get to the adding part, I'm going to take a step back here. And taking a step back here, and so there's a couple of things we first need to know. That I is equal to I. I squared, or if you square an imaginary number, so if you're talking about the square of -1, square root of -1, this actually is just simply -1. So I squared is equal to -1. I cubed is equal to -I. And how is that possible? Well, I cubed is equivalent to I squared times I. Well, I squared, we just said, was -1, so -1 times I, which is -I. Well, I to the fourth. Okay, well, I to the fourth is actually 1. Again, how is this? Well, we just said I squared is negative 1. Well, I to the fourth is I squared times I squared. So that's equal to negative 1 times negative 1, which is 1. And if we repeat this, after every 4, it repeats itself. So now I to the fifth is back to I. And if you were to go on, if you kept on going, I to the sixth would be equal to negative 1, etc. So it keeps on repeating. So if I wanted to know what I to the 20th power is, what is that equivalent to? A very common type problem. I to the 20th, well, we're going to look at this in terms of the 4s. There's 5 I to the 4th, which I to the 4th was 1. So what's 1 to the 5th power? Well, that's 1. Alright, let's get a new page. I to the 9th power. Okay, well, if I take and break this up to figure this out, how many 4s there are? Well, I to the 9th is equivalent to I to the 8th times I. And again, everything that is multiples of 4 is equivalent to 1. So this is then 1 times I. So I to the 231 power. Now this is going to take a calculator. You do 231 divided by 4, and that is 57. So there's 57 times 4. So 57 times 4 is 228. And then we still are left with 3 left over. So I to the third power is negative I. Now how can we do that quickly? Well, if you're looking at one of these, I just did 231 divided by 4, because after every 4 it repeats itself, and I to the fourth is 1. So this answer in my calculator was 57.75. So 57 times 4 is 228, and then I'm left with a remainder of 3. Remember, 3/4 is 0.75. So if it was 0.25, that would equal I. If it was 0.5, that's equal to negative 1. And if it was 0.75, it's I cubed, which is negative I. And of course, if it's a whole number, then it's 1. Okay, so if it's 0.75, when you do that, it's I cubed, which is negative I, in a whole number. So if it's 0.00, then that's I to the fourth, which is 1. And so that's just the real quick way to do that. Alright, moving on. Again, adding. So if I have, say, 5 plus 2I plus 6 minus 3I. This works just as you may suspect. Again, we don't need the parentheses here. They can be disappearing. And the whole numbers, or the real numbers, go together, which is 11. And the imaginary numbers go together, so this is negative 1I. And that's how adding works. Whole numbers, or excuse me, real numbers and real numbers, and imaginary go together. So let's do one more. 7 minus 2I minus 3 plus 5I. Well, now there's a minus here. That makes it a little different. That's going to distribute, so it's negative 3 minus 5I. So 7 minus 2I. Now again, real numbers go together. So 7 and negative 3 makes 4. And negative 2I and negative 5I makes negative 7I. And that's it. That's how adding works. Okay, multiplying. Now, multiplying is just going to require foiling. So if I do 4 plus 3I times 5 minus 2I foiling, just as if it was an x. So 4 times 5 is 20. 4 times negative 2i is negative 8i. So that's the first one. And then if I do this one, this is 15i. And then, of course, negative 6i squared. Now, here's the deal, though. Negative 6i squared can be changed. It becomes, remember, I squared is negative 1, so negative 6 times negative 1 then, so that makes it positive 6. So I have 20 minus 8i plus 15i plus 6. So real numbers go together, so 26, and imaginaries go together, 7i. And that's your answer. Let's try another one. It's just distribution again. So 4 plus 3i, 5 plus 4i. Okay, distribute, distribute. So I get 20 plus 16i, and then I distribute on the bottom, the second one, 15i, and then of course the last one, which is 12i squared. Now I squared again, this part here is negative 1, so that makes this negative 12. So we get 8 then, because 20 and negative 12 makes 8, plus 31i. Okay, one more. Dividing. 7 plus 2i divided by 8 minus 3i. So here's a division. Now a conjugate, remember, is when you multiply and they're identical except the middle sign. And what's beautiful about this is, of course, the middle terms cancel out. And so whenever you're dividing, you're actually going to end up turning it into a multiplication problem. But you have to multiply by the conjugate of the denominator. So again, conjugate is the word there. C-O-N. They're identical except one's positive, one's negative. And the reason why we do that is when we multiply these bottom ones here, and multiply this, the middle term is going to cancel out. So let's do that. 8 times 8 is 64. 8 times 3i is 24i. Normally I wouldn't even do the middle step here. This is negative 24i. And then of course negative 9i squared. This is just the denominator what you're doing, so we've got a numerator up here. So if I clean up the denominator, 24 and negative 24, they cancel each other out. Negative 9i squared. Again, I squared is negative 1, so that's negative 9 times 1, which makes positive 9. So this is 73 as the denominator. Now if I go back to my top here, I had 7 plus 2i times 8 plus 3i. So 7 plus 2i, 8 plus 3i. Alright, so if I FOIL the top out, let's get a new color here. If I FOIL the top out, it's going to give me 56, 21i, and then going bottom. So this is going to be 16i and 6i squared. Again, I squared, if you do not know this by this point in the video, you should know this, it's negative 1. So I squared right here is negative 1. That becomes negative 1. And so that makes this negative 6 here. So I have 56 and negative 6, which is 50. And then this part here is just 17i. Oops, how about 37i? Really good math. 37i. All over the 73 that we already found. So this is your answer. Or you could write it as 50 over 73 plus 37i over 73. So again, your steps on this one, if I go back here, This is what we originally had right here. Took the conjugate, which is 8 minus 3i's. Conjugate was 8 plus 3i. But I can't just multiply the bottom. I've got to also multiply the top. When I FOIL out the bottom, there's no i's left. They're all, when I FOIL out that bottom, they all disappear. The middle ones disappear. Right here. And of course, I squared is negative 1, so that was 73. And then I FOIL out the top, and that's what I'm doing here, and I get 50 plus 37i. Okay, this is imaginary numbers. Again, the only use for them is electrical circuits that I know of. I'm sure there must be another one, but I don't know of any others. There we go.